Hello and welcome to my project on primes, which I call Unbounding Primes. Today we'll be discussing, I call it Unbounding Primes because Yitang Zhang, back in 2014, proved that the limit as n approaches infinity between consecutive primes is less than 70 million. That just means you can't have 70 million consecutive products, or products in a row. So, his problem was that he wanted to not apply a part of the Vinogradov theorem, which is applicable which just says that you can't include large primes as factors in large numbers. Otherwise, this proof falls apart. Well, that's what I'm about to prove. He won multiple awards, including $40 million, and for 2 years he was congratulated and received prizes. Alright, in 4.2 million primes or less, I will show you that the twin prime conjecture's past proofs have been false, including Yitang Zhang's worldwide accepted proof, and all by showing you a multiplication table. And I'll also show algebraically that there are indefinitely innumerable consecutive products, as well as a new proof for unlimited, uniquely dispersed primes. Lastly, I'll entice you with the prime equation, which must be revealed with caution, and I'll show you why later. People say the only pattern to primes is that there isn't one, but there are two patterns I would like to cover in my journal. Alright, the first one is that all the known primes in a list, if you multiply them, and then add or subtract one, you either get a new prime or the product of one. And then secondly, if you add a factor to its product, like how 6 goes into 30, if you add 6 to 30, you get another product, 36, and 6 goes into 36. Alright, so we look at this prime chart. It's our multiplication table that shows our primes all the way from 0 to 30. And so we have this 0. It's going to be our little mark spot. We're starting from 0, and these are going to be the multiples of 6. An interesting pattern of primes is that after 3, whenever you have a multiple of 6, the prime is either going to be less than 1 or greater than 1 from that multiple of 6. And so 31 is going to be a prime number, and it's going to be next to a multiple of 630. It happens with all primes. They're going to be next to a multiple of 6. And so we keep this 0 as if we went backwards 1, and we know that each prime is like a different puzzle piece. This 2 from the 0, this is 2 spots. This 3 from the 0 is 3 spots, etc. It goes all the way. We're going up to 29 for 29. I'll show you that pattern in a second. Alright, so we're going to go ahead and just make sure that this is understood. A factor of the product x times y is x. So it's like 5 times 6. 6 can go into 30. And so, if we add 6, we get 5 plus 1 equals 6, and this is going to be a factor. And if we add 6 again, we get 42, which is another factor of 6. X can go into x times y plus 2. Every time you add x, including to this, you get y plus 3 from the y plus 2 times x. Now we'll go ahead and apply the primorial. This just means you multiply consecutive primes. For example, if you do 5 primorial, it's 5 times 3 times 2. And so you multiply all the primes down to 1, you get 30. Because 2 times 3 is 6, times 5 is 30. And this creates an interesting pattern when we apply the primorial to this. Below we have a table of about 6.4 billion. It's the multiplied first 10 primes, or 29 primorial. And we also have labeled its following products. This primorial will replace the 0 in our previous table and help us visualize it. And the parentheses, I'll go ahead and explain this table. These parentheses are known products. Here's our 29 primorial. And then we just have adding 6. 6 can go into 29 primorial because we multiply 2 and 3. And 2 and 3 make 6. So 6 can go into 29 primorial. Now, notice these 2 blank spots? They are potential primes. But since 2 can go into 29 primorial because it's 29 times 23 times 19 times 17 times 13 times 11 times 7 times 5 times 3 times 2. So we have all these factors of primes going to 29 primorial. We add the 2. We know 2 is a factor that goes into this product, so we know this is a product as well. 3 is a factor, so we add it, and we know this is a product as well. 4 is a is a factor as a product of 2. And since 2 can go into it, we just add 2 again, just like the previous part, how we got the y plus 2. And we were able to show that this is also a product. And then we have the 5 is another prime. All these factors that go into 29 now fill in all these spaces. So now what if we took it to the next step? So as we can see, the primorial of 29 plus 2, that just means we skip that blank space above, leads to a block of consecutive products. And because 6.4 billion-ish plus or minus 1 are known products with factors of 79 and 331, we have over 60 consecutive products. So let's go back to this so I can explain. This is a known product, and so is this. They have factors with either 79 or 331. And so, if we subtract 2, 2 goes into it, just like how 2 goes into 12, we subtract 2, it goes into 10 as well. This pattern always follows. And so, all these multiples of 2 that we subtract are also going to be products. And if we subtract 3, it's also going to be a product. Just like how we added 3, we can do the same rule by subtracting it, and it's still a product. And so, this is what I call the primorial mirror. We have over 60 consecutive products because of the extra 30 beforehand. The primorial mirror. Now, what if we looked at the primorial of the first 4.2 million primes? That's also 70 million primorial, because it's the primes all the way up to 70 million. Now, we'll have a potential primes at those blank spaces next to 70 million primorial, but right after that, that's 70 million primorial plus 2, we'll have 70 million blocked out in a row. We're also guaranteed 70 million more products right before it. And if those blank spaces are products, then, and there's already a large chance that they are, we'll have 140 million and 3 consecutive products. Can you imagine an infinite product blackout? That means the whole table all the way to infinity is just products. We're almost there. And so, here, if this was 70 million primorial, we would have these 2 blank spaces, which are potential primes. But right after that, we add 2, we add 3, we know 4 is already a product, and so, and 2 can go into 70 million primorial. And so, we know this is a product. We get 70 million filled in boxes in a row. And so we're trying to see if we can get a total product blackout. We have a new limit, where n is a large number. As n approaches infinity, the primorial of n plus 2 equals a total product blackout. That's right, infinity products, all in a row. No more primes. But technically, there are still many primes after you do a multiplication of all the primes, because like I said, once you take all the known primes and multiply them, you add plus or minus 1, you either get the new prime or the product with a new prime as a factor. Right, and just to repeat, that's because no other primes can go into it. 2 is the smallest one. 1 is too small. All right, and so the limit means, just to review the limit, it just means to use as many primes as we know, because we have limited knowledge in getting close to infinity. And so we concretely conclude there are infinitely many primes with infinite variance in dispersion. It means there could be any number of products in a row before we get another prime number. This entails that the twin primes, as well as cousins, disperse infinitely. Twin primes are just primes are within 2 of each other, and then cousins are within 4. There is no limit to products in between the primes. And let's see, I just go on here to talk about the prime equation. The prime equation should help us answer questions about that. And then there's one additional interesting pattern we're mentioning about quadruplets. That's 2 sets of twins like 11 through 19, or 101 through 109. That's 11, 13, and then 17, 19. They only appear in the first 10 of 100. So there's another occurrence, and that's in 13,000. Around the beginning of 13,000. All right. Now I'm going to talk about the prime equation. The prime equation. All right. Prime numbers show up in the life cycles of certain animals to avoid predators' attacks on the vulnerable young. They also play a powerful part in our lives. I know the prime equation. It helps you tell which prime it is. So, for example, 29 is the 10th prime. It would tell you that. It would say 29 is the 10th prime, or what is the 100th prime, and it would tell you that as well. I would reveal it in my next journal, but I've been having such a hard time getting these out. I don't know how I'm going to communicate to you people. And so, I would like to first inform you, before I get it out, another application is with encryption, and that's super important. Whether transferring stocks or bonds, using usernames or passwords, or making bank transactions, banks specifically use a 2 to the 11th bit encryption based on the sum of two large primes. So if the hacker had this prime equation, they could hack banks within a week. So I will give banks a week to change their passwords via the news before I announce the prime equation through this publisher, or through this site if I can't find a publisher. Alright, and although there are some equations that help us find primes like Mersenne and Voxstops, they're often unsuccessful and occasionally find a new prime. My equation will answer all your questions about primes, and including twins, and especially when we can take the derivative to find the next primes. Alright, thank you for watching my tutorial on this video. I hope you enjoyed it. I'll go ahead and listen to your questions and I'll answer them. Please post them below. Thank you again for watching.